Now the hardest part of today's lecture is Abel's formula. So if we have two solutions of a linear second order homogeneous ordinary differential equation, then the Wronskian of these two solutions is given by the following formula: is time constant times e to the power minus antiderivative of p of t dt. Well, know that it means that since this part is strictly positive, is e to the power something, it means that this is either the Wronskian is either 0 for all values of t, or is positive for all values of t if c is positive, or is negative for all values of t if c is negative, right? But the Wronskian cannot cross the t-axis, so it is impossible that the Wronskian is 0 for some particular value of t but non-zero for another value of t. Okay? Now let's prove this formula. First, some preparatory work. I'm going to write down what the Wronskian is. So the Wronskian as a function of t is the determinant. By this straight line, I mean the determinant. So this is the determinant of the matrix y1, y2, y1 prime, y2 prime. Right, so this is y1 prime, this is y1, y2 prime minus y1 prime, y2. Okay, then it happens that in order to prove it, we are also going to need to evaluate the derivative of the Wronskian, right? Because the Wronskian is a function of t. So let me find w prime. So w prime is, I'm going to need to differentiate the expression for the Wronskian. So the derivative of y1 times y2 prime is by the product rule is y1 prime, y2 prime, y2 prime plus y1 y2 double prime minus, again by the product rule, y1 double prime y2 minus y1 prime y2 prime. Okay, so then notice that these two terms cancel, and this part is just y1 y2 double prime minus y1 double prime y2. So that's w prime, the derivative of the Wronskian. Okay, so now let me write down the condition that y1 and y2 are solutions of the differential equation. So the differential equation is y double prime plus, strictly speaking, p of t, but I will miss of t, so I'll just write p. But please remember that it is actually a function of t. So y prime plus q is 0. Sorry. Y is 0. So that's the differential equation. So the function y1 satisfies this differential equation, and the function y2 also satisfies this differential equation. So I'll write y double prime plus y prime plus q y2 is also 0. Alright, and now we are going to apply a very clever trick. So in order to exclude y1 and y2 from these two equations, we are going to multiply the first differential equation by negative y2, and the second differential equation we are going to multiply it by y1, and then we are going to add them together. Alright, so the first term is going to be y1 times y2 double prime, that's from the second equation, minus y2 y1 double prime, plus both of them have p, so it is p times the second equation has y1 y2 prime, and the first equation has minus y2 y1 prime plus q. Now the second equation has y1, y2, and the first equation has minus y1, y2. Well, but y1, y2 minus y1, y2 is just 0, so this part cancels. And this equals to 0. Alright? But notice that this is nothing else but the derivative of the Wronskian that we just computed, w prime, and this is the Wronskian itself, w. So, what we see is, what we have just established, is that the Wronskian satisfies the following differential equation as y prime plus p. Remember that p is a function of t, so plus p w is 0. And this is a linear differential equation. It is linear in w. So we can solve it by multiplying with the integrating factor. The integrating factor here is mu of t is e to the power antiderivative of p of t dt. And multiplying by the integrating factor, we get the equation integrating factor times w, everything prime, and the right hand side is still 0. So but then e to the power p of t dt times the Wronskian is a constant, so which means that the Wronskian is constant times dividing by the integrating factor, we get minus integral p of t dt, so which is exactly Abel's formula. Okay, so Abel's formula has been proved. A very beautiful argument. Yeah, so in order to do it, we kind of we wrote down that both y1 and y2 are solutions of the differential equation, and then we applied a clever trick and derived a differential equation on the Wronskian, and then we solved that differential equation on the Wronskian, and then we obtained Abel's formula in the end. Okay, now another theorem, and suppose that functions y1 and y2 are solutions of a homogeneous linear second order differential equation on some interval I. Well, and then let w be their Wronskian. Then there are two possibilities. So either they are linearly independent, so in that case the Wronskian is never 0, or they are linearly independent, then the Wronskian is constant 0. Now let me explain again. So the second part is obvious, and we already proved it. From Abel's formula, it follows that the Wronskian is either constant 0 or is never 0. Well, but we are yet to show that if two functions are linearly independent, then their Wronskian is not 0, because if these two functions are not solutions of the same second order linear differential equation, then it is possible that they are linearly independent, but the Wronskian is still 0. We saw an example of that, right? So in other words, in order to prove it, the only thing that remains to show is that given that y1 and y2 are solutions of a certain second order homogeneous linear differential equation, so then if the Wronskian is 0, then they are linearly dependent, right? So it means that the example that we had here, where the functions are linearly independent but the Wronskian is 0, it means that these two functions cannot be two solutions of the same second order differential equation. Alright? So this is what we still need to show. So let me do it. So assume that the Wronskian is constant 0, and let us get a contradiction, right? So, well, if the Wronskian is constant 0 for all values of t, then the Wronskian at some particular value of t is also 0. Now let me write down the Wronskian. So the Wronskian is the determinant of y1, y2, y1 prime, y2 prime, which is y1, y2 prime minus y1 prime, y2. And now we are going to do a clever trick again. So now I'm going to write something that probably looks strange. C1 y1 plus C2 y2 equals 0, and C1 y1 prime plus C2 y2 prime equals 0. But then let me consider this as a system of simultaneous equations in the unknowns C1 and C2. Right? So if you think of this as a system of equations in C1 and C2, then it is a linear system of equations, and its matrix is y1, y2, y1 prime, y2 prime. So which is exactly the Wronskian matrix. And we are given that the Wronskian is 0, right? So the Wronskian is the determinant of this system of linear equations, and it is 0, right? But when the determinant of a system of two equations with two unknowns is 0, it means that either it has no solutions, or it has infinitely many solutions, right? Or infinitely many solutions. Now, which of the two cases do we have here? So notice that, well, 0, 0 is a solution, because if C is 0, C1 is 0, C2 is 0, then the system is actually a true equality, right? So since it is a solution, it means that the case of no solutions does not apply here, right? Because there is at least one solution. But then it has to be this case, infinitely many solutions. So since there are infinitely many solutions, well, it means that at least one of them is not the 0 solution. So there exists a non-zero solution of this system of equations. Right? So let us take this C1 and C2 satisfying this property. Well, so what we have is that according to, well, the point T0 should be present here, just skipped it for simplicity of presentation, but now it is important, right? So let us consider y, which is C1 times y1 of t plus C2 times y2 of t. Then y evaluated at t0 is C1 y1 at t0 plus C2 y2 at t0, and then according to the system of equations is 0. Then y evaluated at t y prime evaluated at t0 is also 0. At the same time, note that y1 and y2 are linearly independent, which means that any non-trivial linear combination is a non-zero function. So which means that this is actually a non-zero function. As a function of t, it is non-zero. But just at the particular point t0, the value of the function and the value of its first derivative is 0. But then this is a contradiction, because what this tells us is that this function y, it is a solution of the initial value problem. Y of t0 is 0 and y prime of t0 is 0. But at the same time, the 0 function is also a solution of the same initial value problem. So which means this initial value problem has two different solutions, the 0 function and y. And that is impossible because it contradicts the uniqueness part of the existence and uniqueness theorem. So, and since this is impossible, we got a contradiction, and this contradiction concludes the proof. Alright, so let me just clarify these theorems on this example that we already saw in this class. Recall that the general solution of this system of differential equation is C1 times e to the minus 8t plus C2 times e to the 3t. So e to the minus 8t and e to the 3t are two seemingly linearly independent solutions. So let us verify it. So let's find the Wronskian of e to the minus 8t and e to the 3t. So this will be the determinant of the matrix, where the first row is just these two functions, e to the minus 8t and e to the 3t, and the second row is the derivatives of these two functions, so minus 8 e to the minus 8t and 3 times e to the 3t. Okay, so now what we are going to get is 3 times e to the minus 8t plus 3t is minus 5t. Minus 8, so plus 8 e to the minus 5t equals 11 e to the minus 5t. Okay? And what you see here is that this minus 5 is exactly minus p of t from the differential equation. Okay, so that's all material for today, and please